In this video, we're going to look at another application of truth tables. This time we will compare logical arguments and fallacies and use truth tables to decide what we have. So we're returning to a concept that we talked about earlier in this course. When we looked at deductive reasoning and inductive reasoning, we talked about arguments as either valid or invalid. And what we mean by a valid argument is one where the conclusion necessarily follows from the premises, and an argument would be invalid if it's not valid. Right? So here are two examples. In the first argument, we have a couple of premises. All students in this class will pass, and Rachel is a student in this class. And then we have the conclusion, Rachel will pass this class. Right? So we've looked at examples like this before. This is deductive, and it also is valid. So if we accept the premise that all students in the class will pass, and we know that Rachel is one of those students in the class, then it makes sense that she would pass the class. Okay, so this conclusion is inevitable. It follows from the premises. Now notice that may or may not be a true argument. We don't know if Rachel will pass, and the reason there's that question is that if we back up to premise one, not necessarily a true premise there that all students in the class will pass. In the second example, we have one that's definitely a false argument. I think you'll see it as we read through, but it still turns out to be valid. Okay, so here's the argument. Our first two premises, Los Angeles is in California or Mexico. Right? Well, that's true. Los Angeles is not in California, and we're accepting that as a premise. We know it's not true, but if you do believe those two things, if you buy those premises, then can we conclude that Los Angeles is in Mexico? Right? Well, if we believe the first statement, we know that it has to be either in California or Mexico, one of those two places. The second premise is telling me that it's not in the first place, not in California. So therefore, if I believe that it's in one of those two places and it's not in California, the only thing I can conclude then is that it is in Mexico. Right? So that is also valid. If you believe those first two premises, you would have to accept the conclusion. Right? So because it can get tricky to see the validity of arguments when we have this true-false type mess in the way there, sometimes it can be helpful to remove all of the words, look at the argument symbolically, and for our purposes, we'll look at truth tables to try to decide if arguments are valid or invalid. Now, generally, you can kind of rely on your common sense, and many people are good at this. You're good at hearing arguments and hearing if it's valid or not. If you normally can hear TV advertisements and think, well, that doesn't make sense. Or if somebody's in a heated argument and you can hear that they're saying something that really doesn't make sense, you probably have a feel for what's logical and what's not. And that's what we're talking about here. But if you have ever kind of lost someone's train of thought or thought, like, I think that doesn't make sense, I don't buy that argument, but I'm not quite sure why, symbolic logic can be used as a tool to try to help you sort through those things. So here's the steps for using a truth table to try to decide if an argument is valid. The first thing we'll do is write the argument in symbols rather than words, and then we're going to rephrase the argument as a conditional statement. Right? So we're going to use a conjunction between all the premises, and then we'll use an implication symbol for the conclusion. Right? So in other words, what we would be doing is, if, like in the last two examples where we had two premises, we would say, what we want to know is, does accepting premise one and premise two, does that necessarily imply the conclusion? Right? Or if premise one and premise two are accepted, does that lead me to that conclusion in all cases? Right? And I do want to consider cases where the premises are false, or perhaps the conclusion is false, because I would still be able to say that the argument could be logical and valid even if it's not true. Okay? And then I would make my truth table. And in the last step here, what I'm looking to see is when I get to the column for that very last conditional, I want to see if in all cases, regardless of whether the premises, conclusions are true or false, I want to see, is this implication true every single time? Is the conclusion always implied by accepting those premises? Okay. If so, then the argument is valid. If not, then it's invalid. Okay, so here's an example. Emerging research shows that if cancer patients undergo aromatherapy, depression is lessened. One of my cancer patients is reporting a decrease in depression, so she must have undergone aromatherapy. All right, so step one, we'll translate this to symbols first. So the first premise is if cancer patients undergo aromatherapy, depression is lessened. So I'm going to write that as if P, then Q. Okay. One of my cancer patients is reporting a decrease in depression. So that's saying the same thing as depression is lessened. So that's Q again. Okay. And those two things are the premises. And then here's the so. Okay, so that's my clue that the next thing is the conclusion to the argument. So in symbols, usually you write your two premises on two different lines, draw a line below them, and then you write 3 dots like this, and that's the symbolic way to write therefore, okay, or so, or then. Okay, so therefore, she must have undergone aromatherapy. Well, that's just a specific case of my first simple statement, cancer patients undergo aromatherapy. Right, so that means that's the statement P. Right? So in symbols, that's the setup for this argument. I have if P then Q, Q, so those are my two premises, and then I want to know, does that always imply P? Does that mean P? So the next thing to do is to make a truth table to decide. So I'll put 2 columns for the simple statements, and then I'm going to, maybe I should write this too. I'm going to write these premises. What is it that I'm actually trying to look at, my final statement? All right, so here's what we want to examine. We want to look at the 2 premises, right, if P then Q, and Q, and I want to accept both of those. So we put an and symbol between them. Right, and then I want to see if that implies, and we're using a double arrow. It still follows the rules for conditionals, but it does help just symbolically to keep track of what things are the premises and what's the conclusion. Right, and then does that imply the statement P? Okay, so then the rest of the truth table I would follow through with this hierarchy. Okay, and the other thing, I would probably do a big parentheses around all of the premises, because we want to make sure we do columns for all of those before we do this last conditional statement. All right, so we would need columns for, so I'll work in the parentheses first, and even in there's another parentheses, so I would have to do if P then Q, and then I would do the conjunction, so I would do if P then Q and Q next, and then finally I would do that entire statement. Does if P then Q and Q imply P? All right, and then from there we just follow the rules for truth tables, for connectives. Okay, so we have the normal setup for P's and Q's. And then we go through and do the rules for a conditional, if P then Q, so that would be true, false, true, true. Right. And next connective is a conjunction, and I want to look at the if P then Q column and the Q column. Right, so I've got true and true is true, false and false is false, true and true is true, false and true is false. Okay, and then finally, follow the rules for a conditional using the column that I just did. Does that imply P? So I'm going to read those 2 columns backwards. Okay, so I would have if true then true is true. If false then true, that's true. Okay. If true then false, well, that's false. And then if false then false, that's true. Okay, so is this valid or invalid? Well, we would look at the last column, and we would need to see all trues in order for this to be valid. So this is an invalid argument. Okay, so if you read that and right away thought, well, that doesn't really make sense, there's some other conclusion that we could draw, well, then that's correct, and we've just proved that symbolically. Let's look at another example. So we're returning to one of the common forms of deductive arguments, and we looked at this in again earlier in the course when we looked at forms of deductive arguments. So we looked at many of them that took this form of the law of detachment. And just a reminder, here's that form. The two premises would be in the form if P then Q, P, and therefore we can conclude Q. Right? So an example might be if today is Monday, then tomorrow is Tuesday. Today is Monday, and then therefore tomorrow is Tuesday. Okay, so that makes sense. All right, so let's check this, and we want to prove that this is a valid form of argument. So we're doing this symbolically, and that way we've proved it for anything that takes this form, regardless of what P and Q are, regardless of if they're true or false. All right, so we set up the, this is already in symbols, so the next thing I would set up is just the complete implication or conditional that we're trying to examine. Okay, so we want to do all of the premises. Okay, if P then Q, and then set this up as a conjunction. So this one and the next one. And if we had a third or a fourth, we would just keep going and we would do and the next premise and the next premise and so forth. And then I want to see if all of those things imply Q. So I think I'll put a big parentheses, maybe I'll do a bracket. Okay, a big bracket around that. Does that imply Q? All right, so let's make the truth table. So we have columns for P and for Q. And then following the hierarchy, we would do, hey, conditional, because that's in a parentheses, in a parentheses. All right, and then next I would do the and, the conjunction. So if P then Q and P. And then finally the entire statement. Does that imply Q? Okay, so here's the setup. So we have the normal setup for P and Q, and then follow the rules for a conditional, if P then Q. So we've got true, false, true, true. Okay, and then an and statement. So now I'm looking at the P, if P then Q and the P column, those two. So we have true and false, false and true, false and true. Okay, and then finally, does that column, right, if that, then Q, follow the rules for conditional. So if true, then true is true. If false, then false is true. Okay, if false, then true, that's true. And if false, then false, that's true as well. Right. So in this case, in all cases, regardless of if P and Q were true or false, or one of each, and so forth, in all cases, accepting those premises did imply a conclusion of Q. And we can see that because we've got all trues in that column. All right, here's another one. This is called the law of syllogism. All right, so in symbols, it would be if P then Q, and if Q then R. Do those two premises imply, therefore, if P then R? Right. So this is like a little chain of if-then statements, and you can even add on to this with more. But it would be something like, let's say P is the statement, today is Monday. Okay, so if today is Monday, then tomorrow is Tuesday. If tomorrow is Tuesday, then the day after that is Wednesday. And if we accepted those two things, then does that mean that if today is Monday, does that imply that tomorrow, 2 days from now, the day after tomorrow is Wednesday? Okay, so we do have a little chain, and that is true in this case as well as logical. So let's check this using truth tables. So again, we'll set up all of the premises. So we want to accept the premise if P then Q, and if Q then R, and then we want to see if those two things imply that if P then R. All right, so this is going to be our largest truth table yet, so we need to do 8 different rows for P, Q, and R, right, and then we'll lay out all of the columns. All right, so we've got P, Q, R, and then in the bracket we've got 2 parentheses, so we'll do the 2 parentheses first, if P then Q, if Q then R, and then we have the conjunction for the bracket, so if P then Q, okay, and if Q then R, okay, and then finally we have the entire statement, and I think I'll just write like the conditional there, that symbol. Okay, so we'll need to do that last. Okay, normal setup for P, Q, and R. All right, there it is, and then we'll follow the rules for conditionals, so if P then Q, so true, true. Actually, why don't I just look through and find any that are true followed by false. So I've got 2 in these 2 spots. So false, false, and then the rest are true. Okay, and then if Q then R, so same thing, I'll look through, I've got a true, false here, and here, and the rest are true. Okay, so that would be true, false, true, 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 false, true, true. All right, then I have an and symbol, and I'm looking at the 2 columns I just did. So let me look through for any that are true, true, and those are going to be true. Everything else is false. And I've got a true, true, and then 2 more true, true, so true, true. All right, and then lastly, I want to see if, I need one more column, don't I? I want to see if this whole thing implies if P then R, and I didn't actually make a column for if P then R yet, so let's squeeze that in. If P then R, and then we'll do the final conditional last. Okay, so if P then R would be if true, true, if true then false, true, 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 false, and then the rest begin with false, so those are all going to be true. Okay, so now I'm ready, so I want to do if this column with all the premises, then this column if P then R. Okay, so again, the rules for conditionals. So true, true is true, false, false is true, false, true is true, false, false is true, true, true is true, false, false is true, 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 true. Whoops. Okay, so we can see we ended up with a column. Sorry, video got cut off there. So we ended up with a column that are all trues, so that means that this argument is valid. Okay, we'll look at one more here. This is a fallacy. It's an invalid argument. It's a pretty common one, so it gets a name. It's called the fallacy of the inverse. And the inverse statement is if you were to look at the negations of both the premise and the conclusion. Right? So these would be arguments that would say, well, if P then Q, well, not P, so then that means not Q. Right? An example would be like the statement, if today is Monday, then tomorrow is Tuesday. Okay? Well, today is not Monday, so tomorrow is not Tuesday. I think I actually picked a bad example there. Mostly because it is confusing, so it is true in this case. But let me try to pick one that's not true. How about, if today is Monday, then I am at work. And then we would say, well, today is not Monday, therefore I am not at work. And I think it's a little bit easier there to see that this can be invalid mostly because you can think of an example that contradicts this. You can, just because today isn't Monday doesn't necessarily mean that you'd be forced to conclude you're not at work. Okay, we didn't say that Monday was the only day that this person works. Okay, so let's make a truth table so that we can confirm that this is invalid. Just because we accept these two premises does not necessarily mean that this conclusion is the case. So we want to do our truth table for if P then Q and not P, and then we want to see if accepting those premises implies not Q. Okay, so we've got columns for P and for Q. Okay, and we could do the hierarchy and do negations first, or we could start with everything that's in parentheses. Maybe I'll go with that option. So we would do if P then Q next. Okay, and then negation of P. Right, and then the other connective in that bracket. So if P then Q and not P. And then I also need a not Q. And I would do that before I get to the final conditional. Right, so there's kind of the hierarchy. We did the whole bracket first, then the negation, and then finally this last conditional. And I'll just write the conditional symbol there. Okay, so we've got the setup for P and Q. False, false, true, false, true, false. And then follow the rules for if P then Q. We've got true, false, true, true. The column for not P, so we would have false, false, true, true. Okay, and then follow the rules for a conjunction of the last two columns that we just did. So true and false is false, false and false is false, true and true is true, true and true is true. And then not Q, so go back and do the negation of the Q column. So that would be false, true, false, true. And then finally, does this column imply this column? Okay, so false, false. False implies false is true. Okay, if false, then true is true. If true, then false, well, that's false. And if true, then true, that's true. All right. So in most cases, 3 out of 4, this would be a valid statement, or this would accepting the premises would lead to that conclusion. But there is a case where that doesn't happen. So the premises don't always lead to that conclusion. So that's why this is an invalid argument, and we would call that a fallacy. Okay, so we've checked some common argument forms, and we've done a few that were longer, and you'll do some practice problems where you try other common fallacies or arguments, and then also some longer statements as well, arguments where it's not as obvious to see in words or even in symbols right away if the argument is valid or invalid.